Welcome to this explainer. Today, we're diving into what I honestly like to call the ultimate superhero of data science algorithms, support vector machines, or just SVM for short. If you're starting your machine learning journey totally from scratch, you are in the perfect place. We're going to unpack exactly how this incredibly powerful tool works to organize messy data, making the complex completely understandable. Okay, here is our roadmap for today. We'll be looking at the perfect boundary, anatomy of an SVM, the secret weapon, tuning the engine, and finally, real-world superpowers. Now, don't worry if the math sounds intimidating right now. We're going to start with some super simple geometry and then naturally build our way right up to those amazing real-world applications. Section 1, the perfect boundary, finding the maximum margin. So let's dive into this by picturing a really relatable visual puzzle. Imagine you've got a graph, right? And it's scattered with a messy cluster of red dots on one side and blue dots on the other. Your job is simple. Draw a line that perfectly separates them. But how do you draw the perfect line? I mean, you could slash a line right down the middle, or maybe slightly to the left, or on a steep slant. The truth is, there are literally infinite possible lines you could draw, which unfortunately means there are infinite wrong ways to do it. Now, what's truly fascinating is how support vector machines solve this exact problem. SVM doesn't just guess or pick some random boundary. It finds what we call the maximum margin hyperplane. Sounds fancy, but it just means it's looking for the one single perfect dividing line that has the absolute largest possible distance from the nearest red dots and the nearest blue dots. It is truly one of the most elegant mathematical solutions in all of machine learning, purely because it creates the safest possible buffer zone between your data. Section 2, Anatomy of an SVM. Meet the hero's powers. Let's completely demystify the vocabulary of this algorithm and translate these kind of intimidating terms into plain English. First up, the hyperplane. This is simply the decision boundary that separates your classes. If you're looking at a standard flat 2D graph, the hyperplane is really just a straight line. If you step up into 3D, well, it's a flat plane. Just think of the hyperplane like the median strip of a highway that perfectly and safely separates two opposing lanes of traffic. Next up, support vectors. And honestly, this brilliantly illustrates the sheer efficiency of this algorithm. Support vectors are those critical data points sitting closest to your hyperplane. They are literally holding up or, supporting the boundary. So here's the crazy part. These are the absolute only points that actually matter. Seriously, if you went in and erased every single other data point that's far away from the boundary, the hyperplane wouldn't change one bit. Finally, we have the margin. The margin is the actual physical distance between that highway median, our hyperplane, and those nearest support vectors from each class. And let me tell you, SVM is absolutely obsessed with maximizing this exact distance. Why? Because a wider margin massively reduces overfitting. It guarantees that when your model encounters new, unseen data out in the wild, it has a really strong ability to generalize and make the right prediction. Section 3, the secret weapon, the kernel trick. Now, it is super easy to draw a straight line when the red and blue dots are neatly clustered on opposite sides of a graph. But what if the data is just a total mess? Like, what if the red dots form a tight little circle completely surrounded by a ring of blue dots? A straight line absolutely will not work there. We have two approaches. A linear SVM handles data that can be separated cleanly by a straight boundary. But for that messy, curved data, we need a non-linear SVM, which deploys our superhero's ultimate secret weapon, the kernel trick. This builds into something truly magical. The kernel trick is essentially a reality-bending mathematical maneuver. Here is how it works. Step 1, it takes that impossible, inseparable 2D data. Step 2, it projects that data straight up into a higher dimensional space, like 3D, and it does this without even explicitly computing the heavy transformation math. And step 3, in that higher dimension, the data points spread out, allowing our SVM to easily slice a straight, flat hyperplane right through them. When you project it back down, impossible separation suddenly becomes perfectly easy. Now, there are a few distinct flavors of these kernels depending entirely on your data shape. The linear kernel is for your standard, easily separable data. The polynomial kernel is fantastic for curved boundaries, and the sigmoid kernel acts a bit like a neural network, but pays special attention to the RBF, or Gaussian kernel. This one is your absolute go-to. It's by far the most popular choice for handling complex, nonlinear data. Section 4, tuning the engine, math and mechanics. Okay, don't panic at the equation W transpose X plus B equals 0. We're just going to peek under the hood for a quick second to see how we control this powerful engine. X is just your input data, B is a baseline bias,
and W is the weight vector, which basically dictates the angle of your boundary. Now, the mathematical formula for the margin is actually 2 divided by the magnitude of W. So if our big goal is to make the margin as massive as possible, our ultimate mathematical goal is to minimize the magnitude of W. That's it. That is the beautiful underlying math of SVM. And here is the truly great news for beginners. Deploying this in Python is incredibly approachable. Using scikit-learn, you literally just import SVC. But, and this is absolutely crucial, take a close look at the second bullet point, always scale your features first. Our source material makes it abundantly clear that SVM is highly sensitive to the scale of your data. If you don't do feature scaling, your performance will tank. But after that, you simply train with model.fit and predict with model.predict. When you're writing that code, you have a few specific dials you can turn to tune the engine. These are your hyperparameters. You select your kernel, your gamma, your degree for polynomials, and whether you want probability estimates. But the absolute most crucial dial to pay attention to here is C, the regularization parameter. A high C means you want fewer misclassifications on your training data, but in exchange, you'll get a narrower margin. A low C gives you a wider, much safer margin, but it might allow a few more misclassifications. It is all about perfectly balancing that trade-off. Section 5, Real-World Superpowers, Evaluation and Application. So, where does this superhero really shine? Well, SVM is incredibly effective in high-dimensional spaces. It actually works well even when your features vastly outnumber your data samples, which happens all the time in things like text classification. It's absolutely fantastic for small to medium data sets. And remember earlier how we said it only cares about those support vectors? That makes it incredibly memory efficient because it only has to store those few critical boundary points, not the entire massive data set. But you know, every superhero has their kryptonite. SVM can be painfully slow to train if you throw a massive data set at it. It is also extremely sensitive to noise and outliers. Literally, a single rogue outlier can dramatically shift your support vectors and completely ruin that perfect boundary. Also, unlike a simple decision tree where you can just follow the logic, an SVM can be a bit of a black box. It's difficult to visualize or interpret directly, and finding the perfect kernel requires a whole lot of trial and error experimentation. But despite those few weaknesses, the raw power of SVM is completely undeniable when you look at these high-stakes real-world applications. The exact math we just explored is out there right now acting as a spam filter in your inbox. It's running face recognition software. It's analyzing complex gene expressions to identify disease patterns. It is actively identifying malicious network activity to stop hackers in cybersecurity, and it's literally classifying medical imaging to help doctors detect cancer. That brings us perfectly to this wonderful summary quote from our sources. The idea of maximizing the margin gives SVM exceptional generalization on unseen data, making the impossible possible in higher dimensions. It truly is an elegant, mathematically beautiful tool that takes chaotic, messy data and finds absolute perfect order right within it. Now, we've spent all this time today focused on the pure geometry of drawing boundaries. But what if we threw out geometry entirely and used pure probability instead? Well, in our next explainer, we'll be diving headfirst into naive Bayes, which is an algorithm that uses probability theory to make surprisingly accurate predictions with very minimal data. You definitely won't want to miss it. Thanks so much for joining me on this explainer, and as always, keep learning.